So you got your typical HTTP request and web scraping code, and you're wondering how fast it is. Let's try sending 50 requests.
6.5 hours later.
42 seconds. That's great! Except it isn't. Let's test another approach, sending the same 50 requests. 2 seconds? But how? Is it magic? Not really. Let's find out. So let's go over this notebook which does web scraping and HTTP requests in multiple approaches. This notebook will be provided down in the description so you can test the code yourself. So what exactly I'm trying to do? I'm web scraping a different website, as you can see. They all provide the same information. They all are literally the same, just with some differences here and there, but they do the same. So I'm doing a post request using the normal request library, and I'm using a payload that I'm having the setting number on. I'm also using a header that is included in the URL referrals dictionary. So once I get an OK response, all I do is just send my response as text to the extraction function, which I'm going to be going over right now. So what is exactly the extraction function? It basically takes this response and put it in a beautiful soup constructor. Also, it initiates an empty pandas data frame, as you can see, and it just scraps the results and put it in this emptied data frame. And that's about it. So let's test out the code and see exactly our function gets score and given it this seeding number. So as you can see, it does its request, it does its web scraping, and put the result in a beautiful pandas data frame. Great. So how long does this process take, and maybe even find ways that we can improve the speed of the code? So this time it in the beginning is a line magic, and you can read more about line magic. I will leave a link in the description that describes the line magic and the cell magic that you can use in your Jupyter notebook or your Kaggle or Colab, whatever notebook you're using. They can work there, but they cannot work in normal Python. So this time it line actually runs this function multiple times and gives you the average time it takes to run it. So by running it, you can see that it takes a while, and it runs 7 runs, right? And the average time was about 0.24 seconds, so about a quarter of a second. So another thing we can do to do more examination is to find exactly what are the sub-function or processes that takes this time. So by using another line magic, which is a prun or profile run, with limiting it to only the first 15 processes, we can figure out exactly what takes all this time. So let's run this code. And as you can see, the first couple processes are related to the request library. So the pandas or the beautiful soup, the web scraping bar literally takes nothing. What takes the most time is the calling of the request functions and its sub-processes. So let's try to minimize this time. But first, let's establish a better testing methodology before we jump into another approach. Let's actually try 50 requests instead of just one, and to measure this out and then compare it with another approach. So if I run this code down here, it's gonna actually send 50 requests using the normal typical synchronous or sequential approach, and we'll measure out its timing. So let's test out. So as you can see, it took about 13 seconds to run 50 synchronous approach, the sequential typical way you go through in your HTTP request library. Let's try to improve that, shall we? So when we talk about speed in Python, usually the 3 keywords get tossed around, which are the multi-threading, multiprocessing, asynchronous. I'm not going to be going over them thoroughly. However, if you want to know more about them, I will leave a link to a great article that explains each and every one of them. In our use case, we will be using the asynchronous approach because it's the most optimal way for our case. So to start using the synchronous approach, there is two libraries you need to import. One is the AsyncIO, another one is the AioHTTP, which we will be using them instead of the request library in our case. So what exactly is the asynchronous approach and how is it different than the traditional approach that we used it earlier? By the way, the traditional approach is called sequential or synchronous approach. So let's go over the synchronous approach and try to understand exactly what it was doing. So we are sending a multiple request and we're doing web scraping and pandas, but how exactly is the code running? So as you can see here, first of all, we are sending a request to the server. However, there is some waiting time, right? This time is waiting time. We are not doing anything in this period of time. We are just waiting for the server to respond to us and give us our HTML back. So there is time that we are losing. We are literally just standing still, doing nothing, waiting for the server to respond to our request. Then we can proceed on and start doing the web scraping, and once the web scraping is done, we make another request. However, we also have to wait before we get our response, and so on and so forth. The asynchronous approach solves this problem brilliantly. Let's go over it to discover how it works. So we are still sending a request to server. However, this waiting time that we are not doing anything on, we actually will start to send another request. As you can see here, we are sending another request to the server, and by doing that, we are also checking on if we got a response from the first request. If we got a response from the first request, then we will go over and start our web scraping and pandas. But if we didn't still get a response, we can actually do a third request to the server and wait for the response. So we are doing a lot of requests in our free time that we are not doing anything on. However, we still check on our older request to see if we received the response or not. If we receive the response, we will keep on and proceed with the web scraping and pandas code. So this is exactly how the asynchronous approach works. It utilizes the waiting time efficiently to make our code run much faster. So back again to the code, as you can see, there is a lot of things that we added to be able to run our code in a synchronous approach. First of all, we have to add the async before our function, and also we have to open a session. This line opens a session and it closes it once the function is done. And we still do the same thing. However, there is another keyword we need to add, which is the await keyword, and we need to add it in a line that will have some waiting time. If your line of code will have a waiting time, then you have to add the await keyword before it. I'm also using the await keyword here because I'm passing the response text to the extraction, which does the web scraping and pandas. So I'm still waiting for it. So in any code I'm waiting for, I will have to do the await keyword before it. So let's try to test it out, running exactly the same 50 requests and see how much of improvement we can gain. So about 5 seconds, down from 13 seconds to only 5. So about half the time it needs to run the 50 requests. That's a huge improvement. There are even more ways to improve the code using the asynchronous library in Python. Let's go over them too. So in a third approach, we will be using asynchronous concurrently, which means we will be passing all of the requests to the server in the same time. And we can do that because we know the nature of our request. We can put all of our requests in a list as a coroutine. And by the way, you can know more about coroutine and our concurrent approach in the link in the description, a great article written in Twilio that explains this whole phenomena. In simple words, we will have a list of all the tasks that need to be done, passed to the asynchronous concurrent function. So let's take a look at the concurrent code and see exactly what is the difference. As you can see, it's similar to the previous one. We have a function that is first defined by async, and we got our session here opened. We have an empty pandas data frame, and we got this task variable. This task variable actually calls the get task functions, which you can see right there. Get task function actually initialize all of the seed we pass to the function will be initialized, and we'll be adding it to the list. So this list contains the coroutines, not the actual response, but the coroutine. It's like a list that contains exactly the task that you should be doing, but it's not the task itself. To run the task itself, you have to wait to use it, the await function, and you pass it to AsyncIO.gather, and you add this star because you are passing multiple tasks, not just one task. And again, just run the code, and don't forget to add the await before the response to get your function right, and then that's about it. Let's test it out. So let's run the same 50 requests and see how much of an improvement we can gain by this concurrent asynchronous approach. So the code literally just took 1 second to run all of the 50 requests. This is a huge improvement over the synchronous or even the normal asynchronous approach. The code will be available in a description, so make sure to give it a look and test it yourself. The timing can be a little bit different depending on your internet and server quality at this time. Anyway, I really hope you enjoyed, and since this is YouTube, I will have to remind you to like, subscribe, and leave a comment and all of this stuff, but I really hope that this was useful for you. Anyway, see you next time. Goodbye.